So hopefully you've had a look at the oh, this works. Okay, I can have the video and the screen share. That's great. So I made this specifically to help with the control this week. Excuse me 1 second. Karsten, please don't do that. Okay. And I hope you've had, I should have added here that you should try the control first, even if you had to stop, then at least that would help you appreciate where we're going with this TD or how it relates to the control. Okay, so the first question here, as always, I was hoping to start with something a little bit simpler, a little bit more familiar. We know what the what the geodesics are. I think someone was trying to, yeah, Davey's trying to get in. Okay, welcome, Davey. So we're just getting started here, and so the you can do a lot of things on the sphere, even though it's a different manifold. It's a different type of geometry. There's no time on the geometry in Riemannian geometry. It's all spatial, but nonetheless you have geodesics, and they're just the great, what we call the great circles. So the equator is an example, but all the longitude lines on the sphere are the great circles. They're basically the biggest circle you can draw on the sphere, and it doesn't have to, of course, the sphere is, oh, okay, thank you. The sphere is totally isotropic, so the where the equator is just corresponds to our choice of a coordinate system, and the geodesics are independent of that choice of coordinate system. So we know that, in other words, we know the answer ahead of time for the sphere. So I hope that helps. And okay, I can't quite do this at the same time. So the thing to do is start with the geodesic equation, and for that you'll need these two Christoffel symbols. So I've written out the geodesic equation in general here, where lambda is just some affine parameter. It sounds like a fancy term, but it just means that we've parameterized the curve in such a way that the magnitude of the tangent vector doesn't change along the curve. And you always have the choice of doing that, so we might as well just make that choice. If not, we'd have a non-zero right-hand side related to the fact that the magnitude of the tangent vector is changing. Okay, so let me remind myself of the equation, or the question. we're asked to demonstrate that a circle with theta equal a constant. So we're in spherical coordinates, and theta, excuse me 1 second. Karsten, that's too noisy. My students can't hear. So theta is the polar coordinate, and phi is the azimuthal coordinate, and theta is not equal to the equator, because obviously when theta equals pi over 2, we're at the equator. So which is a geodesic. Whoops. Okay, so let's we have theta equal to a constant. So we demand that phi has to be non-zero. So I already had one question from one of you, which was that in the control, the question was, well, all the spatial coordinates are fixed. So how can we have a geodesic? But don't forget that time is another coordinate in space-time, in four-dimensional space-time. So the time is moving. It's only the spatial coordinates that are fixed. Okay, but here we demand that d phi d lambda is non-zero. Otherwise, we just have a fixed point. We don't even have a curve. A geodesic is a curve. So at least one of the coordinates has to be moving. Has to be, when I say moving, I mean changing, taking on a range of values. Okay, so we have d phi d lambda, just notation, let's call it phi dot to keep it simple, and demand it's not zero, but d theta d lambda is zero. So this geodesic equation is actually in the case of a sphere, we have a two-dimensional manifold. So our indices take on two independent values. We can call them 1 and 2, or theta and phi. I think it's easier to just use the coordinates themselves. So let's start with alpha equal to theta. Sorry. So this refers to this upper free index in this equation. Mu and nu, I haven't talked about them yet, but they're not free indices. Those are dummy indices, so they just stand for the sum. So we choose our value of alpha and then write out this equation, including the sum, and then we choose a different value, the other value of alpha, and write out this equation. Okay, so when alpha equals theta, we have x becomes x theta. Let's just call it theta, and we'll have a theta in the upper part of the Christoffel symbol, and then we have the sum over here, over mu and nu. Now you have various options. You can decide. Let's start getting rid of the terms that are zero. I suggest one thing you can do is look at the Christoffel symbols themselves and ask, when is the Christoffel symbol with theta upstairs, when is it non-zero for what indices downstairs? And there's only one. It's quite simple in the sphere. We have this guy here, theta phi phi, and it's minus sine theta minus cosine theta times cosine theta. So we can just substitute that in here. We can sum over all values of mu and nu, and they're all 0 except when mu and nu are both phi. And then it equals that. So let's just substitute that in. So we have d squared lambda d squared d lambda squared of theta plus this particular Christoffel symbol, the only one that was non-zero, times the corresponding here, it'll be x phi, because the mu corresponds to the mu here. So that has to be x phi, but let's just call it, x phi is the phi coordinate. So we have d lambda, or d phi, d lambda, which let's call it phi dot. And then nu had to be phi as well. So we have the same term here. So it's in fact phi dot squared. And then let's see, theta was constant. So d theta d lambda is 0. And so the second derivative is also 0. So we have 0 for this term plus this one particular term times phi dot has to equal 0. Now it becomes important, the fact that we said phi dot was non-zero, right? Because that is non-zero here. And then we have this some non-zero term times this thing. And again, now we have to stipulate that theta is not pi over 2. And so neither cosine theta nor sine theta is 0. Except, I guess, when you could go up to the pole, right? Did I mention that here? Yeah, except you could go to theta equal to. Oops, no. Yeah, there is a solution when theta equals 0, that you're at the pole. So on the sphere, that corresponds to the North Pole. Theta is the what we call the co-latitude. So it's 90 degrees minus the latitude. I think that's right. Anyways, it's 0 degrees when you're at the North Pole. It's 90 degrees at the equator, and it's minus it's a pi when you're down at the South Pole. So that's 90 degrees and 0 up here. So the what corresponds to the North Pole is the solution. But then you're at a point, even if your phi, your longitude is changing, you're at the pole. So you're it's a singular point in the coordinate system, and you're not moving. You don't have the possibility of moving, so that's not really a solution. So that is that constitutes a proof that this candidate solution is in fact not a solution. It's not a geodesic. What do these lines look like? Lines with the polar angle equal to 0. Well, those are the they're the latitude lines on the globe, right? The line, there's 49 degrees. We call them parallels in English, right? The 49th parallel is the line that separates Canada from that little country south of Canada. And it's also the line that goes through Brest. It's about, pretty sure Brest is about 49 degrees north. Okay, I should stop here. That's like, it's simple. I hope you thought that was simple, but it's very important what we just did. I think that's pretty much the control continue there, but applied to a more complicated space-time. So I want to make sure that you all understood that. Can I just maybe I better check the chat. darn. Yeah. So please ask questions if you had any. Okay. So Malo, thanks Malo. How do we know phi d lambda? Well, we don't know. I think we don't know phi d lambda. I think that's the answer to your question. But notice we didn't need it here. All we needed to know was that phi d lambda was not 0. And as long as that was not 0, that's good. So it was just kind of mechanical in a way. We systematically worked through the geodesic equation until we got to here. And then we said, look, phi d lambda is not, which is phi dot, is not 0. And then, so that's not 0. And then we have this term, which is not 0, except at the pole, but then we found another reason why we can't go to the pole. So that's a contradiction. And once you have a contradiction, you know you haven't solved this equation. Does that answer your question? Yeah, okay, good, thanks. Thanks for communicating. Yeah, please don't, you can even, I'll try and unmute your microphones. You're welcome to ask your questions in French or in English. And yeah, so maybe I can just try and recap here. The general, if you're asked, as I do in the control continue, and there, and I might, by the way, I might ask this on the exam too, because I think it's an easy question to ask because, or easy in the sense that I think it's faster for you because I give you the candidate solution, you plug it into the equation and you look for a contradiction. That's a little bit faster than prove. Like the other option is I can ask you, prove that a geodesic is, Carson, careful, get down. Oh my God, my child was about to fall or risk to fall off the table. The problem with proving, well, it's also a good question to ask, prove this is a geodesic, but then it's much longer because you have to show that it satisfies all of the geodesic equations. So if you're in 4-dimensional space, you have 4 geodesic equations to prove. And so it's just more work, it takes more time, and during an exam, time's very limited. Yeah, so the general strategy, just if you're trying to prove it's not a geodesic, you just get to a contradiction and then you stop because you've shown it's not a solution. Okay, so let's, with that in mind, how about you now have a go at, hopefully you've tried this already, but I want to give you a few minutes to at least think about, or with this new information or potentially new information, try and address this next one. Demonstrate that when you are at the equator, so when the polar angle is pi over 2, show that is a geodesic. So I think even if you didn't sort of know where to get started earlier, it should be clear now. So I'm going to come back in a few minutes. And feel free to ask questions. during this time. I'll monitor the chat. Yeah, but I'll give you a few minutes to work on that. I think I will. Okay, I guess I'd like to sort of help you along here. So of course we go back to this equation and we set theta equal to pi over 2, and then cosine is 0, and that equation is valid. But see, we're not done yet because we're in a two-dimensional space, and we have two geodesic equations. The alpha, remember, could take on the values theta and phi. Excuse me. Please keep the noise down, guys. Come on, I'm trying to teach you. Sorry.
Trying to teach you. Imagine saying that in your class.
Okay, so but it's only two-dimensional, so there's only one other value. It's phi, and so you write that in the equation. Let's write x phi as just phi, and so then we have this geodesic equation. So the coordinate we're taking the second derivative of is phi. The phi appears upstairs here, and then we're summing over mu and nu. Oh, you have a choice. You know which ones of these are non-zero. So you could just substitute. You know it's only phi that's changing because theta is fixed at pi over 2. But let's continue with the Christoffel symbol idea. You can go look at the Christoffel symbols and say, I need a phi upstairs. But there was only, well, here's the subtle point, okay? There's not just one, there are two. Even if I only write one, see, I'm a little bit lazy here, right? When I give you the Christoffel symbols, I say that the non-zero ones are the following. Oh, no, I wasn't lazy. This time I wrote both of them. Okay. Okay, my children have found a new game, but it's very noisy. So, so yeah, so let's, when we do our sum here with the Christoffel symbols with phi upstairs, we have 2. So don't forget. I know from asking this question, you know, in previous years, people always forget the there's a well. You're only changing the order of these terms here. You know, theta dot, phi dot, and the other way around. And these Christoffel symbols. What am I doing here? I got confused now. I got confused because for some reason I've got, I think I have a mistake here, don't I? So I have the so we have the one with phi upstairs, and it's this one. I think I made a mistake here, didn't I? This should be phi dot, or the second derivative of phi. Yeah, I'm sorry. This should be with not theta upstairs, but phi. Yeah, so this is all wrong. I think I better fix that. Alors, ça devient ne trouve aucun problème ici. Well, I just found a problem. On ne trouve. Okay, so I think it's all these thetas have to become phis. Sorry about that. Replace. Now, hopefully I can just, yeah. Okay, so I changed this to a phi. I'll just continue be a little bit careful. Oh, God. No, that's right. But that needs to be changed. Okay. Okay, I think I got it. Yeah, so the phi, it has to be phi upstairs and it has to be phi there. Phi here, phi upstairs. Yeah, so these two Christoffel symbols are actually the same because it's symmetric in the lower two indices. And here we're just changing the order of the product of real numbers. Well, that doesn't change. A times B is equals B times A, right? So that's just becomes 2 times this Christoffel symbol. That factor of 2 does not appear in this equation. Because see, well, it just doesn't appear in this equation. But when the phi is different from when you have theta phi or phi theta, then you need the factor of 2 there. Okay, so that's where the 2 comes from. And that it doesn't actually make a difference in this equation, but it does. It would if I asked you to find the period of the circular orbit around the Earth, or so that would be for the moon's orbit around the Earth, or for a planet around the sun. You can find the period using this geodesic equation, but you can't forget the factor of 2. Okay, so theta dot is 0. So even though these other things are non-zero, theta dot 0, so that term drops out. So we have the second derivative of phi equals 0, but that just means theta dot. Let me fix that error. That means phi dot is a constant, right? And so there's no problem there. It just means that phi is moving, and it's the derivative with respect to our affine parameter is constant. So that puts some restrictions on this equation, but and that restriction arises because we chose an affine parameter, but the rest is sort of details here that don't sort of interest us so much. We're just, we've proved that the point is there's no contradiction. We've covered all the all 2 geodesic equations for this 2-dimensional problem. We haven't found a contradiction. We had this equation, which is fine, and we had the other one was just trivial, 0 equals 0. So there's no contradiction. So that is a solution. As we know, the equator, it's just saying the equator is a geodesic on the sphere. Let's get into a more interesting space-time, well, sphere's interesting too, but a more, let's say, less familiar space-time. Let's look at the, well, I'll let you read the question. if you don't mind, I think we should let's go through this together. So it's exactly the same idea as the second equation or second question that we just addressed. Prove something is a geodesic. Of course, we're in a different space-time, and and it's a four-dimensional space-time. So we have the same geodesic equation, but it looks the same, but the free index alpha takes on the four values t, r, theta, and phi. And so we're going to have to write out, and we're being asked to prove something is a geodesic. So we have to verify that all four of those geodesic equations are valid, are validated. There's no contradiction. So here I've decided to be a little bit more explicit about what's non-zero. So I said we had a circular orbit at the equator. So at theta equals pi over 2 and r is a constant. So then we have the other components. So we have two non-zero components, or potentially non-zero. We might find that, phi, we won't, but I mean, hang on. Yeah, we could, well, it depends how explicit I was about the solution, but I mean, in principle, you could have a geodesic where only one of the coordinates is changing. I mean, we just found them, and that could apply here in space-time. But in practice, it doesn't, because well, I just said circular solutions, right? So they could be time-like or they could be space-like. I've made a choice. Well, and I've given you a hint that they have a period, and we're supposed to calculate the period. So they're going to be they're the classic orbits of the sun. The Earth around the sun. So it's a time-like geodesic. In principle, it didn't have to be, but so we have two things changing along the geodesic. We have the coordinate time and the azimuthal angle, and r is constant and theta is constant. And I've written tau here, which is suggesting that I'm using proper time. So I'm assuming it's a time-like geodesic. We can find later that indeed it is time-like if we want. But first, let's just find the geodesic. So we have to let alpha take on all four values. So we start with alpha being t. You could start anywhere you like, but might as well be systematic and start with the first one. or there is no order, right? It's just that's the way I guess it's convention to have time as your 0th coordinate. It's actually not a universal convention, but it's becoming more, at least in the Western literature. The Russians used to put time as the last coordinate, which is quite sensible actually. Um, but anyways, so we put t in for alpha. Let's call xt just t because that's what it is. And then we have to look at these Christoffel symbols to find the ones that are not 0 when we have t upstairs. And it happens to be this one. But it has tr downstairs. So there's an error. I just found an error in my solution, which is embarrassing. Can someone tell me what the error is in this equation? So it's this equation here is wrong. Exactly. Very good, Milo. Yes. Yes. So I'm going to try and fix that before I forget. Yeah, so we needed a 2 there, right? Because you can change the order of t and r. But it didn't actually affect the results because r dot was 0. So we have dr dt, or sorry, dt d tau is constant. I know this must look funny, right? The coordinate time, the derivative of the coordinate time with respect to the proper time. But it's just it's a question of I guess time dilation, right? The coordinate time is the global time that we use to sort of give every space-time event in our space-time a unique time value, a time coordinate, but it doesn't. It has nothing, almost nothing to do with the actual time that's measured by a clock. Yeah, they're just different things. It's just like longitude on the globe. If you think about the longitudinal coordinate on the globe, it's it doesn't tell you the distance, right? The distance or the difference in longitudinal coordinate between 2 points. It could be 1 degree longitude, but 1 degree longitude can correspond to a distance between 0 and something like 110 or 111 kilometers. It's 111 kilometers at the equator and 0 at the North Pole, and 0 at the south, and any value you like in between, depending on the depending on the latitude. And you have the same sort of thing going on with coordinate time. Coordinate time is very useful. It tells you the coordinates of a point in of events in space-time, but to find the proper time it's a different question. Well, and it depends on this derivative here. Depends on the constant in the equation. Yeah, and I'm saying so there's time dilation and it's related to to gravitation here, just like we saw in the experiments the Italians did in the Alps. Okay, so we found one geodesic equation which just simply says the TD tau is constant. Let's move on to the next one. Alpha equals R. Uh, in fact, we have 4 Christoffel symbols here in the. I'm getting all these from the big list that I give you. I expect you to know how to calculate these things from the metric, but I would, um, on an exam, I would typically give these to you, or I might ask you to calculate one of them just to show that you know how to do it. But there's just too many of them to make an exam question out of. Find all the Christoffel symbols of Schwarzschild or something. It's just too much work. Oh, by the way, I confirmed with um, Jan Legrand, the guy who does the astrophysics, that he always, or he will this year, and apparently all years, he lets you have your notes or course material during the exam. I'm going to do the same thing. So even if I didn't give you these Christoffel symbols, you could look them up. But if you needed them on the exam, I would certainly give them to you so that you wouldn't waste time shuffling through your notes. The exam's going to be in January, so hopefully it'll be in presentiel. Hopefully you'll be able to do it in person. So we look for R on top. See, we have all 4 of them. They happen to all be they have the double coordinates at the bottom, but it's all 4. So here they are. We're not too concerned actually about their values, but we have, you just plug that in to the geodesic equation with R here. And so in principle, we'd have the 4 terms without the factor of 2 because it's t dot squared here, phi dot squared. But we only have 2 of the say the velocity or 4 velocity components that are not 0. So we only have these 2 terms, and R is one of the coordinates which is fixed, right? It's a circular orbit. So the radial coordinate is fixed. So we just have a balance between these 2 terms, if you like. And so I've just decided to, I'll do a little algebra here. You move this on to the right, divide by minus gamma r theta theta, and take the square root. And I guess a mathematician would say I've just made a mistake here, and I've chosen a root, right? I could have taken a minus root, but it's not really interesting, right? It's just that the orbit goes this way, or well, I guess it's interesting in that there's no asymmetry. The orbit can go one way or the other way, but that was kind of obvious, or it's obvious from the symmetry of the space-time. You can have an orbit clockwise or counterclockwise around this space-time, and I chose one where the angle phi is increasing with time, with proper time. And you can work out that it's actually interesting to plug in these Christoffel symbols and manipulate them, and because it simplifies, and this is beautiful in a sense. We can actually find from this the let's use this because it was part of the, well, you could just say, okay, so we've got a geodesic. We could look at the other equations. There's no contradiction here. We could move on to the next, the two other geodesic equations. But let's pause here and find the period of the orbit, because we actually have enough information to find the period of the orbit. In fact, I'm going to let you just read that and see if you can follow along how we get the period of the orbit. And note this beautiful formula at the end, which looks just like the Galilean or was it Kepler? I think Kepler just rolled over in his grave, right? I was about to give credit to Galileo for Kepler's discovery. This is Kepler's equation for the, or no, shit. Yeah, it is Kepler. It's Kepler. I mean, Kepler didn't know that it's Newton's constant, obviously, because he was living before. Kepler just knew this m times g is a constant. We now know it's the mass of the sun times Newton's constant. Yeah, so this is the Kepler, t squared is proportional to r cubed. Yeah, I'll let you work through that. Okay. I hope you've had a chance to look at this. Now we can just sort of return to the definition of what d phi dot and t dot are. They're the derivatives of these coordinates with respect to the proper time. And then we can, if you like, if the mathematicians aren't listening, we can just multiply by d tau, right? But if they are listening, then we better do an integral with respect to proper time, I suppose. And then we have this equation, and then we can integrate again both sides, and we have some finite period. This is a differential of the coordinate time, and if we integrate that, we get the well, I guess I've integrated phi over a cycle of 2 pi. So I've done a full orbit, and then the coordinate time is the period of the orbit, and this is oh darn. Let me. Oh, I know. I have to do this. Yeah, now you have the reference here. I guess I took this. This is a question I've used in a previous year when I taught the course using Schutz's book. But you can find this as the circular orbit in Hobson's book for Schwarzschild. Well, I guess it doesn't really matter. Yeah, so it's maybe this deserves a comment here. This looks very familiar to Keplerian. It looks like Kepler's formula, but it should be noted that the physical interpretation. Well, if we applied this to the solar system, this basically we've just reproduced Kepler's orbit. But if this were a black hole and the radial coordinate was just outside the event horizon, then the physical interpretation of these things in this general relativistic context would be very different from the the pre-Einsteinian physics because well, as we were discussing earlier, t here is the coordinate time, not the proper time. It's not the time you would measure with a clock as you go around that orbit. And r is not simply the distance from the orbit to the center of the solar system. It's the radial coordinate, and which as we saw in the class is different from the physical distance. Now the solar system is almost flat because the sun it's curved enough to give us some Newtonian dynamics, some gravitational effects that are consistent with Newton, except for tiny little perturbations in the orbit of Mercury, but that were noticeable actually before Einstein, but barely. And so in other words, the gravity in the solar system is extremely weak. So to a very good approximation, this period would be the period we would measure with the clock here on Earth as we do our circular orbit around the sun. And so we'd find 1 year here. By definition, it's 1 year, right? For the orbital period. For our 150, this is the orbital radius, so it's to a good approximation, the actual orbital radius of the Earth. It's 150 million kilometers, actually. So this does work in practice in the solar system, but the physical, but it's much more general. I guess that's the point. This is more general. It applies in a black hole space-time. We're not done yet, right? And this is important because if I ask this question on the exam, and I have asked this a question on exams, you have to finish. You have to show that there's no other contradictions. Now it's pretty easy, let me say the hard part of the question has been done, but you need to finish off here. You have to let theta alpha equal the two other possible values. So we have the two angular values, theta so we have 3 Christoffel symbols, which so one of the Christoffel symbols is non-zero in general, but is 0 at the equator. That's the one we saw earlier. Then the 2 other Christoffel symbols, well, they have an r in them downstairs, so that means it's multiplied by r dot, but r dot 0 because it's a circular orbit in question. So those 2 go away. And then theta was a constant, so its second derivative is 0. So this becomes trivial. 0 equals 0. And I don't know why I don't have the last one. I think I was, well, I was a little bit lazy and I said the two other geodesic equations are trivial. That was maybe not a good decision. I should have finished because I demand that of you to be to um, complete here. So I should, but we can do it. Let's do it together right now. So we'd have d squared phi d tau squared, and then we'd look up here and we'd find all the Christoffel symbols that are have phi upstairs, and there's 2 here, and there are 2 here. But let's go ahead, and we know we're at the equator, and theta equals pi over 2. So this one, in fact, takes on the value 0 at the equator. So in fact, we only have these 2 here. Okay. So let me I'll be explicit here. Oh God, you're gonna see my horrible French because I always, well, anyways, la dernière équation. So I change theta to phi, and well, that's fine. So this is the last equation. So il y a, on a dit 4 symboles de Christoffel non zéro en général, mais theta égale à pi sur 2, on n'a que 2. Non zero. Peut-être you don't use the trait d'union comme en anglais. So I'll put that here, and it was I've forgotten now. It's the R phi one. So it's R phi, and I'll just go ahead and write 2 there. And I'll write R dot phi dot R dot phi dot R dot phi dot. Yeah, so 2, because these are not the same. and then we have now it's okay, but r dot is 0. So we can go, we can acknowledge that because r is constant, the r dot goes to 0 here. And so we're led to the conclusion that phi dot must be a constant. And but I think we already knew that, or phi dot is a constant. No, maybe we didn't know that, but we knew it was related to t dot through this equation. So this tells us that but no, I guess I think we had, yeah, sorry, we had t dot is a constant. So from this equation, this equation 21, phi dot is constant because r is constant, and these are just constant parameters. So in fact, we knew that, and so so we would just say that this is consistent with the above. I think you say cohérent avec les résultats précédents. Right? So that's it for that that demonstration. So that is actually more work than what's expected of you in the control continue this week. So I'm hoping that you have all the information you need now to do that that exercise, or that control. Are there any questions? Okay, I'll take that as a positive sign. Of course, it might arise that issues come up when you apply this to the question that I asked you. I think it was to show that when you have fixed spatial coordinates in Schwarzschild, you don't have a geodesic. So what that means, I can give you the physical motivation for that. It means if you're, the gravitational field here at the surface of the Earth is to a very good approximation Schwarzschild. We're just ignoring inhomogeneities in the Earth, then the fact that it's not exactly a sphere, but I mean it's a very, very close to a sphere, and it's rotating, but that's a second order effect. So our gravity here at the Earth is to a good approximation that of Schwarzschild, and so but if I'm just sitting here in my living room, my spatial coordinates are fixed. My temporal coordinates not. Time is going forward, and I'm getting more gray, getting older as time goes on here, which I can't help, but I can keep my spatial coordinates fixed, and I'm not following a geodesic. And so the point is, something has to be stopping me from doing that, and it's the fact that I'm sitting on this sofa here, and so that's why I feel the force. I feel the force of gravity because I'm not in a free falling frame. I have fixed spatial coordinates, and so I'm accelerating in the reference frame of or I'm accelerating in this curved space-time. So I feel the effects of gravity. Yeah. So trying to think. So this is not. We're going to look at another space-time called the Friedman-Robertson-Walker, and in there, it becomes interesting. I have a question in the chat, so I'm going to try and get to that now. In Friedman-Robertson-Walker, it's interesting that there is the corresponding question. If we have fixed spatial coordinates in Friedman-Robertson-Walker, which describes the universe, then those are geodesics. So that would be a good exam question because I'm asking you to prove something is a geodesic. Okay, how do we prove that? Okay, good question. How do we know equation 21 is 0? It's not equal to 0, Melo. It's not. We didn't have to show everything was 0. Oh, well, I mean, I had 0 on the right-hand side here, but I moved I hope you can still see I'm circling this, or well, actually, no, if you like, what I did was I moved this term here with the t dot to the right-hand side. And that's why I picked up that minus sign. And then I divided through by this Christoffel symbol. That's how it got on the bottom. But these things are squared, so I took the square root. And as I said, the mathematicians would complain that I didn't explain that I took the positive root, et cetera, et cetera. So yes, I have 0 here, but then I just solved this equation. Okay, I think, yes, we did prove it's a geodesic. This is the geodesic equation, and we solved it. We solved this equation. And this is the solution. Okay, good. So just for the others, I want to say, look, Melo is thinking this through, right? And he wants to make sure he understands this. And this is exactly what you all should be doing. Everybody should be doing the same thing as Melo here. Asking, do I understand this? What, and I think it's through really working through it and trying to discuss it with me that you can. Well, I think you can figure these things out without me, but it's just that I think it's faster if you take advantage of me being here. In fact, this is the way I'd like to, a preferred way to teach, I think, is to let you try and work through these things and then just ask me questions. But listen, we have a bit of time. I scheduled an hour and a half for today, but I think it's maybe what we should do is stop here. And then unless like ask a question quickly if you have one, but if you don't, or if you can't think of anything now, go ahead and work on the control continue, and then send me an email, and we can discuss it further. Or I'll respond by email, or if you want, we can set up a Skype or a Zoom meeting. Okay. So I'll email you this so that you have a copy of this file, because I think I didn't give it to you yet. But yeah, how about just in the time that it takes me to do that, I'll stay online here. But if not, I'm going to sign off here and ask you to just contact me if you by email if you have any questions about the control, and or if you manage to get it done early, send it in, and then that's a good idea, because then I'll correct any problems, and say if there's time, I'll send it back to you, and then you can fix those, without penalty. Okay, let's stop there, and yeah, I do have the kids this weekend, as you see, so I won't be quite as available, but I will make time to, let's say I'll look tomorrow at noon, and I'll look again at 6 p.m. to see if there are questions, and submissions to read, and yeah, I'll check it those 2 times, at 12 p.m. and 18 p.m. Okay. Okay. Good luck with that. Don't hesitate to contact me. Okay. Bye for now.